This will be the first video where we look at the chemistry of carboxylic acid derivatives, and in this first video we're just going to look at some general reactivity trends that we see across the series of derivatives. Okay, so up here at the top are the most common types of carboxylic acid derivatives that we deal with. Okay, all right, far here on the left is the acid chlorides. Okay, let me change that to the pen, sorry. Okay. All right. These are our most reactive of the carboxylic acid derivatives. Okay. Less reactive than acid chlorides or anhydrides, than thioesters, than regular carboxylate esters, which we just refer to as esters, and finally amides over here on the right are the least reactive of the carboxylic acid derivatives. Okay, the acid chloride and anhydride are not really stable functional groups because they react with just plain old neutral water without any acid or base additives in it. So they're not all that common in nature because, well, nature is full of water, and any water that comes in contact with these functional groups would destroy it. Okay. If we look at the groups over to the right, these are stable in water. These incur quite a lot in the environment and very useful in many biological processes. And we're going to spend some time with esters and amides looking at their physical properties as well. We're not going to look so much at acid chlorides and anhydrides because they're usually, you generate them and react them immediately, so they're not useful, or we don't normally think of them as stable compounds. Okay, all right, so as we go to the left here, we're increasing the reactivity of these. Reactivity to what? Well, let's just say water, for example. Okay, or any nucleophilic substance. Okay, so the acid chlorides are the most reactive. The amides are the least reactive. All right, reactivity is the opposite of stability. So as we go to the right, we find that our derivatives are becoming more and more stable. Okay, less reactive to water and other nucleophiles. Okay, another important relationship with this diagram here is that any compound that we have pictured up here can be converted into a compound to its right very easily. Okay, so anhydrides, for example, it would be very difficult to convert an anhydride into an acid chloride. But an anhydride could be very easily converted to a thioester, an ester, or an amide. Okay, so example, in the bottom here, all we need to do is treat this with an amine. We'll look at that reaction a little later, and this would easily turn this into the amide. But as far as are there reactions that turn esters into acid chlorides? It can be done, but it's a multi-step process. You have to turn it into the carboxylic acid before you can turn it into the acid chloride. Okay, what's the origin of this relative stability deal here? Okay, and so chlorine, shown here, is inductively electron withdrawing. We say that because it has an electronegativity that's higher than carbon. Okay, but it does have lone pairs that can interact with the carbonyl group to some extent. Okay, so we can draw the resonance structure right here. Actually, that's got too many. No, let's see. Yeah, that has too many lone pairs. So let's get rid of that extra lone pair. it can stabilize the carbonyl group through resonance, but because this bond here, the pi bond here, isn't really all that strong, it's a 2p with a 3p element. Those types of pi bonds aren't really all that great. We say that the inductive effect for chlorine is more important. Its resonance stabilization is much less important. Okay. Nitrogen is a very different situation, though. Okay, so we have the lone pair here. Can stabilize by resonance like that. Nitrogen's, it also has electronegativity that's higher than carbon, but what we find is that this pi bond that we generate by drawing this resonance structure is actually a fairly strong pi bond, and the resonance effect ends up being quite appreciable here. So in nitrogen, the resonance effect wins out, and thus the effect of nitrogen is that it's tremendously stabilizing to the carbonyl group through this resonance interaction that I drew with the arrows. Okay. All right. So the deal is that with the esters, we have an oxygen there. The resonance effect is still strong, but not quite as important, and it's even less important with thioesters and anhydrides. And it's this resonance interaction that we're looking at here that kind of explains the order of reactivity for the various carboxylic acid derivatives. The strongest, or the case where we have the strongest resonance amides, produces the most stable functional group, the amide functional group. Okay. All right, so the key reaction here is going to generally be classified as this process right here. It's called nucleophilic acyl substitution. Let me just draw in the lone pairs here. Okay, so in nucleophilic acyl substitution, a nucleophile is going to come along, it's going to attack the partially positive group. In the ketone and aldehyde chapter, this immediate adduct that we get called the tetrahedral intermediate was a perfectly stable compound. But when we have the carboxylic acid derivatives here, our Y group is a potential leaving group. So a second step happens, and this leads to the substituted acyl product. Okay, the net result is that the carbon Y bond has been replaced by the carbon nuc bond. All right, this looks like a classic substitution reaction, but this is not the SN2 reaction. This is an important thing to remember. This reaction, nucleophilic acyl substitution, has an intermediate. The SN2 reaction does not. It's a concerted process. Okay, so that's why carbonyl group is sp2 carbon, but we're doing the substitution reaction just fine. So this old adage that I've been using in this class, you can't do SN2 reactions at sp2 carbon, it still holds. We can do substitutions, but they don't necessarily follow SN2 mechanisms. All right. In most cases, this is our slow step, and this is our fast step. Not always, but there are a lot of cases where the tetrahedral intermediate can be observed spectroscopically. It has enough of a lifetime, but in most cases its collapse occurs before you can do any sort of isolation. Okay. All right, so that one at the top is a purely nucleophilic substitution. We can activate the process with acid. Okay, so if the carbonyl group first reacts with an acidic substance, we generate an activated acyl compound. Now our nucleophile can add, just like before, but because the carbonyl system is activated, much weaker nucleophiles can now do this chemistry. Okay, let's go ahead and draw the lone pairs there. All right, so we're now going to kick this out this way through our tetrahedral intermediate's now neutral, but it can still eject the leaving group. we're going to generate a protonated acyl compound, which is going to lose the extra proton to finally make what's equivalent to the same product that we see up there at the top. Okay, and we're going to see both of these variants, mechanistic variants, used in most of the reactions that we talk about in this chapter. Okay, so first let's look at acid chlorides. An acid chloride reacts rapidly with neutral water. You don't have to add any base or anything to it. You can just take distilled water and react it with an acid chloride, and a reaction occurs. Let me just write that reaction out. The reaction with water generates the carboxylic acid and HCl. That's a balanced reaction equation right there. Okay. All right, so we're not going to discuss the physical properties since this is not really all that common of a natural substance. Okay. How do we prepare acid chlorides? All right, this is the reaction of choice. SOCl2 reacts with a carboxylic acid to make the acid chloride, and it generates two byproducts, sulfur dioxide and water, and sulfur dioxide and HCl. SOCl2 is not the only reagent that'll do this. Here's some alternative reagents: phosphorus trichloride, phosphorus pentachloride, and oxalo chloride, which we write this way. Its structure is basically this. It's the diacid chloride of oxalic acid. Okay, we've seen acid chlorides before. They do one reaction in the first half of the class. This is the Friedel-Crafts acylation, right? Okay, so as long as our ring is not terribly deactivated, at least as reactive as chlorobenzene, we can react it with an acid chloride and aluminum chloride, and this is an ortho-para director. Okay, so this produces predominantly the para and ortho compounds, but mostly the para, because it's a sterically better site than ortho, but almost no meta comes out of this reaction. Okay, all right, let's look at some other reactions. This reaction we've already introduced earlier, but when we introduced it, it was just an equation. Now we're going to look at its mechanism. Okay, so an acid chloride, an alcohol, and pyridine makes an ester and makes a pyridinium hydrochloride. Okay, let's say if you leave pyridine out, you get kind of a much slower reaction. We'll just look at that. Okay, this forms a lot of HCl, and this is often damaging to the product. So the reaction is almost always done with pyridine, but you still would get a reaction if you didn't have pyridine in it. It would be much slower, and it would be kind of a much harsher conditions. Okay, so here's what happens. Our alcohol adds to the carbonyl group, and I'm keeping it as a protonated because we have this situation where pyridine, even if pyridine were not present, you'd still get a reaction. Okay, this gives us a tetrahedral intermediate. All right, we can write two mechanisms at this point. In mechanism number one, I'm going to just go ahead and expel chlorine this way. This gives me protonated ester, and this is not a very stable compound. This is quite acidic. The pyridine in solution will remove this proton, and we'll get our product. And we'll get pyridinium hydrochloride. You can see that in this last step, pyridine is reacting with H+ to grab a proton. All right, the alternative mechanism. Okay, let's just forget that I drew that arrow, is to go ahead and transfer the proton. Okay, this is what we call the self-neutralization. Okay, this proton would be much happier if it were at the alkoxide, right? We'd have a perfectly neutral compound with no excessively acidic or basic sites, so the self-neutralization is going to occur very readily. At this point, we can now displace the chloride, and this would produce this. These are both really viable mechanistic pathways. All right. In the last step here, the pyridine is going to remove that proton, and you'll get the same products as you would have gotten by the other mechanism. All right, so if we want to make a thioester, we're just going to substitute a thiol for an alcohol, and this will work just fine, okay, if we do that. All right. Pyridine, its effect is a little bit more complicated. This is what I'm going to present here, but if this were a graduate level class, we'd probably write an officially different mechanism. Okay, pyridine is actually going to do the initial nucleophilic acyl substitution after we form an adduct with pyridine. Let me just draw it out here. Okay, it's going to add just like that. It's going to produce the product. We're going to generate this. There's no lone pair here. And this is intermediate is very reactive because there's no stabilization of the carbonyl group whatsoever. And it's also carrying a positive charge, so this is making it very attractive to a nucleophile. All right, this is adding here. We're getting the alkoxide, displacement. Pyridine comes along, and the mechanism in the later stages is just like before, and it removes the proton. Okay, so pyridine actually has an activating effect on this reaction. It's not just an HCl absorber, but any of these mechanistic possibilities we presented probably are just fine. Okay, amide formation is another key reaction for acid chlorides. All right, so notice here that I have 2 moles of the amine here. All right, so this is reacting with the acid chloride. This is making the amide. Okay, so ammonia gives a primary amide. Okay, and it forms NH4Cl as a byproduct. Okay, because of the formation of this byproduct, that's why we need 2 moles of the amine. All right, if we take a primary amine, we get a secondary amide. Same general reaction equation, same general byproducts as the one to its left. We get the protonated amide as the byproduct. And if we take a secondary amine, we get a tertiary amide. Okay, if we have a tertiary amine, that's an amine or with 3 R groups, we can't make an amide from that. All right, sometimes our amine is precious and we don't want to waste a whole mole of it. So if you do that, if that's a concern, you can add another base in there. Often it's triethylamine. And again, this will not form an amide, so you can add this, and this allows you to use just 1 mole of your amine, and if you do that, you'll get as your byproduct triethyl ammonium chloride. Okay, All right, so let's look at the mechanism for this one. All right, this is just nucleophilic acyl substitution. Our nitrogen lone pair attacks the carbonyl group to give us our tetrahedral intermediate. Okay, we're displacing the chloride. This gives us now the substituted compound in our base. Our base is going to either be hydroxide, triethylamine, or another molecule of our amine that we used to do this reaction, and this is going to produce the amide. Okay, and whatever base we used, we get the protonated form of that base. If it's hydroxide, we get water. If it's triethylamine, we get triethyl ammonium. Okay, we'll briefly look at the chemistry of anhydrides. Anhydrides, I'm just going to make a statement about their chemistry. They do the same thing as acid chlorides, but just not quite as vigorously. Okay, so they're somewhat tamed acid chlorides. All right, here's how we make symmetrical anhydrides. You just take a carboxylic acid, 2 moles of it, and heat it to a high temperature. Water will, to some extent, be formed, and as the water is formed, you just get rid of it by boiling it out or something like that, and this gives you the anhydride. Okay, so it's driven to equilibrium by Le Chatelier's principle. In most cases, an anhydride will react with just plain old neutral water to regenerate 2 moles of the carboxylic acid. There are a few examples of water-stable anhydrides, but for the most part, they do react with water. Not quite as vigorously as acid chlorides do, but they're unstable in neutral water solution. Okay, this is how we make a symmetrical anhydride. If we want to make a mixed anhydride, the only reaction we can do is nucleophilic substitution using a carboxylate anion and an acid chloride, and this will make the mixed anhydride. My anhydride there wasn't very mixed, but yeah, so you get the compound with a R2 group there. All right, cyclic anhydrides are a little bit more stable, especially if they have 5 or 6 membered rings, and we make these by taking dicarboxylic acids and heating them to high temperatures. In most cases, we don't make our anhydrides. The anhydride is usually bought, not made. There are some examples where we make it what we call in situ. We generate it, then use it immediately, but for the most part, we don't make anhydrides. We buy them. Okay, let's see, we're not going to discuss their physical properties because they're not all that common of a functional group in nature. Again, they're due to the intervention of humans. Okay. All right, so if we look at the reactions of anhydrides, as I said before, we can sort of sum it up by saying it's the same as acid chlorides, but slower. All right, so if we take an amine, okay, we're going to do an acyl substitution here like so. This is going to get our tetrahedral intermediate. It's just going to fall apart like before. Our leaving group's not chloride, it's in this case benzoate, and this is going to produce the byproduct, the amide. Recognize one problem with anhydrides, and that's that we waste 1 mole. We're going to waste one of the groups at oxygen. Okay, we're going to so with the acid chloride we got rid of a chloride, but the leaving group here is actually half the molecule, so it's a little bit more wasteful than the acid chloride. Okay, we can take an alcohol and pyridine. This will produce the ester just like the acid chloride would, and it, instead of evolving pyridinium chloride, we evolve pyridinium, in this case benzoate. All right, if we have a cyclic anhydride, our acid leaving group, or our carboxylate leaving group, is still going to be part of our molecule. So take, for example, this compound here known as phthalic anhydride. If we treat this with methanol and pyridine, we're going to make the ester at one of the acyl groups. And the other acyl group will become an acid chloride. Sorry, carboxylic acid. Okay, so this reaction here is going to produce this compound that contains both an ester group and an acid group in it. Okay, so we're going to end this video by just doing a few problems here. We're going to predict the products of each of these reactions. All right, so the first one, we're treating this phenol with an acid chloride. And I'm just going to make this notation here that there's no aluminum chloride here. So phenol, you recall, can do the Friedel-Crafts acylation. Later in this class, we do talk about the chemistry of phenols, and we'll revisit this aluminum chloride versus no aluminum chloride issue. But we're just going to look at the reaction with pyridine. This is strictly an ester formation and produces that ester right there. All right, in the next one, we're going to treat it with a compound that has an OH and an NH2 group. An important thing to remember here is that this is more nucleophilic. Okay. It's more nucleophilic or more basic, so the product is going to be this product right here. The nitrogen is more nucleophilic than the oxygen. We can also look at this from a stability standpoint, but I'm not sure that's the major governing factor here, but the amide carbonyl group is much more stable than the ester carbonyl group. So this is the thermodynamic product. All right, in the second one, we've got a dilemma, or this third one here, we have a bit of a dilemma. Which C double bond O is going to be attached to an NH2 group, and which double bond, or which CO double bond is going to be part of a carboxylic acid. Okay? What we can really look at here is that there's an important resonance stabilization of the top carbonyl group. All right, so this one is stabilized by resonance, the top one. The bottom one is not stabilized by resonance, so this one is going to be more reactive. And so when we do this reaction, we're expecting to produce the product that you see over to the right, the one where the NH2 is in the bottom carbonyl group. Okay? And in the last one, we're taking, I guess, butyric anhydride and pyridine with an alcohol. And we're just going to make the ester. And remember that we basically wasted one butyric acid unit when we did this process, but this should be our product, okay? And we'll say okay, so we'll have that product there. Okay, so this is where I'm going to stop this video, and we're going to, the next one we'll look at esters, then the other one we'll look at amides. Okay.